So welcome everyone to one of our astrophysics talks. This time we have Ronan Kerr from University of Texas at Austin. He's a PhD candidate there. Had his bachelor's degree from University of British Columbia, if I'm not wrong. Please correct me if so. His study is mostly on young stellar populations around solar neighborhood, and his research interests are nearby star formation, young stellar associations, molecular cloud dynamics, and massive white dwarfs. So Ronan, thank you very much for accepting to giving this talk, and please go ahead. Thanks.
Yeah, sure thing. Thanks for having me. Happy to be here. So my project is on what I call the SPYGLASS program, which is an acronym that I'll get into a little bit later on. But first thing, let's go over my contents briefly. I'll start by introducing what I do, go over some current results that I have in preparation and upcoming work through my studies of young populations, going into an expansion of the survey that I'm doing to larger distances, and then just going over the top level lessons that we can learn from all of this. So first thing I want you to know is that, oh, hold on, is this, stop going to the next slide. Oh, it went twice, there we go. So yeah, my study is fundamentally a story about star formation. So what I want to start by doing is putting in your head this idea of what star formation looks like. So you start with this cloud of gas that begins as this expansive cloud, and then it condenses under the weight of gravity. And you start seeing these dense regions appearing as the dense gas condenses. Those can get dense enough to form stars. And as stars form, you begin to get additional feedback processes that begin to shape how that cloud moves forward. So what I want you to get into your head is how the creation of stars can begin to form new epochs of star formation and can guide how a star formation event moves forward. So there are two ways of studying star formation if you talk in the most general form. So one is using gas dynamics and active formation to get this picture of star formation. And I'm personally somewhat partial to this approach because my first study in astronomical research was doing exactly this sort of thing. You basically get this big data cube of certain molecules and certain certain velocities of motion from these clouds, and you can use all this to piece together exactly the way in which different segments of gas are moving, which gives you this beautiful dynamical view of how the gas is moving, and you can get this incredible view of how the gas is forming into stars in real time, which I find incredibly beautiful. However, the big limiting factor behind this is that you're only seeing a snapshot. You're only seeing it at one point in time. So if you want to really go back and look at how an entire star forming event took place, this isn't the way to go. So what we end up doing is using the stellar populations route, which is using the stars themselves, that is this fossil record of star formation left behind to construct a history for a star forming region. So why might we want to do this? So we get that long history that we don't get from watching active gas interviews. So that's the fundamental thing that you want to know here. And that allows us to, first of all, investigate slow processes. So let's say there is a 20 million year period over which a star forming event takes place. If your star forming event takes place with that long of a period of time, you need to have this long record to draw from to be able to figure out when, let's say, star formation begins and ends, whether there were pauses in between bursts of star formation, various processes that may have taken place like that. And there's also the fact that because of the fact that we only have like a limited number of star forming regions that are easily accessible to us, we may have a better chance of detecting very fast processes that aren't common enough for us to be able to detect them in terms of active star formation at any given time. So lots of reasons why stellar populations are useful. And the reason why it's been possible to use stellar populations to study star formation in recent history is entirely because of the Gaia spacecraft's incredible addition of almost 2 billion stars for us to investigate. And And there are a few things that Gaia gives us. So first of all, we get distances and motions. And that allows us to construct this 5-dimensional space velocity view of how stars are moving. So we're able to determine whether stars are currently in space together, and we're able to determine whether they're moving together. And those are the two key elements of figuring out whether stars are part of a common population or whether they aren't. And we also get the ability to have photometry as well. So we get the luminosities in various different color bands through Gaia as well. And when you combine distances with the photometry, you get luminosities. And those luminosities are different depending on the age of the star. As stars collapse off the main sequence, they get more and more, they contract more and more until they fall onto the main sequence. And during that time where they're in a more bloated state, they have a higher luminosity compared to similar stars of older ages. So if you're able to get this, these luminosities for all these stars, you can figure out whether they are young just by looking at them. And through Gaia, we have almost 2 billion stars to do this with. And because of the fact that Gaia covers the entire sky, we can do this without any restrictions. We just look at the entire sky. We can cover massive associations with no significant spatial biases. So that brings us to what my acronym was. Stars with photometrically young Gaia luminosities around the solar system. It's pretty much exactly what the acronym says it is. So we're looking for young stars using Gaia luminosities nearby to the sun. And we do it using a Bayesian approach where we estimate the probability of a star being young based on a model population that represents the solar neighborhood. And through this, we find about 30,000 stars that are young. This is in a recently published paper that I released over the summer. In this one, we identified about 30,000 stars with a probability greater than 10% that the age is less than 50 million years. So you can see that these more or less fall in this G and K range. Actually, never mind. I was going to try to switch to a laser pointer, but I can't figure out how to do that right now. So
we can see the mouse perfectly fine, no problem.
That works great. Thank you. I appreciate it. So yeah, it's in this region that we see most of our young stars, and this is the K and M region for the most part. We basically are able to detect up until about G8, which is where the subgiant branch begins to dominate the population, and we can no longer reliably identify a star as being young. But K and M stars are most stars, so that gives us still a massive population to work with when we're trying to identify young populations. And because of the fact that we have those motions and those positions from the Gaia spacecraft, we can start to do clustering. So this is identifying populations that are co-moving and co-spatial in the sky, and using this to identify populations. So we get quite a few groups in this study that are already well known and well characterized. These include SCO-SEN, the Taurus complex, Perseus OB2, Perseus OB3, the near edge of Orion, and a few of the Vela associations down in this region. So lots of known populations, but you might notice that there are quite a few here that are not really known. In fact, they possibly outnumber the stars or the populations that are well characterized. So these include populations like Cepheus far north, all these Taurus Orion groups down here, Canis Major north, Aquila east, Ophiuchus southeast. There's quite a few of them here, as you can see. So that brings us to the first big prong of what I'm trying to do with my current exercises in working with the SPYGLASS program, which is taking individual populations and doing case studies on them, seeing what these populations can tell us about how star formation progresses. And we have quite a few available populations to do that with. And there are a few reasons why doing this sort of study is useful. First of all, nearby groups are in demand for membership studies. So there are quite a few researchers that like doing studies on young stars. One of the ones that's been of a lot of interest lately to me is there are some researchers that are using my populations for planet hunting. So there's a researcher at Caltech, his name is Luke Buma, and he's been doing hunts using the Kepler catalog. And it turns out that I actually have a population that I'll briefly mention later on that is directly in the Kepler field. So he's been looking for planets in these populations, and because of the fact that we have ages, based on the population that we see, based on isochrones, based on dynamical ages, we can begin to, understand the age of a planet, which is very useful for people doing that sort of planet study. And nearly all of the associations that were first seen or really first highlighted in SPYGLASS 1 have no targeted study or census to date. So we are in a very good position to be the first to really characterize these associations and allow these populations to be used in future studies. And there's always a possibility that you see new patterns in star formation. So let's say, are there patterns in metallicity, or are there patterns in formation location? There are various features of these star formation processes that may be of interest. And part of the reason why we want to do this study, that is us as researchers at the University of Texas at Austin, is that we have all these observational resources. So Gaia covers the astrometry and photometry, which allows us to get 2 dimensions of that velocity vector in space, but we don't have that in and out velocity. We don't get that radial velocity, and radial velocity is critical to complete the velocity vector for these stars and really gives a full view of what's going on. So UT actually has 2 sets of resources that are accessible for use for these sort of studies, and they both involve Echelle spectrometers, or Echelle spectrographs. And we have the 2.7 meters Cull-Coude spectrograph at the McDonald Observatory, which is an excellent facility. This is in West Texas. And we also have 4 nodes of the Las Cumbres Observatory, which gives more Echelle spectrographs. Sorry, I'm having trouble with that word apparently. Because there's more Echelle spectrographs at 4 different nodes around the world, and this allows us to get access to the Southern Hemisphere through South Africa and through the Chilean nodes. And because of the fact that we have entire spectra available to us, we can also identify youth indicators, and these include lithium, which actually depletes as stars get increasingly old and can be used as a very reliable age data. And we also can get H alpha, which is an indicator of accretion. So 2 very useful indicators of youth right there. So now I'm going to go into what we're currently working on in these studies of young associations, young case studies. And the 2 that I'm most close to getting released now, these are both very far along in the in-prep stages. It is the populations of Cepheus far north and Fornax Horologium. So both of these are large enough to host substructure, which has not been previously identified for groups this size prior to the SPYGLASS work. So it's going to be interesting seeing what we can get in terms of substructure in these regions. They're both close, so observations are feasible all the way down to the premium sequence turn-on, which means that we can assess objects above the premium sequence turn-on based on their radial velocities and whether they're co-moving in three dimensions. And we can assess stars below the premium sequence turn-on according to their high position elevated above the main sequence. And we can also test run analysis methods that we would want to use in harder to study environments, let's say SCO-SEN, where we have, rather than a few subcomponents, we might have, let's say, 40 or so. So it gives us a good opportunity to test run methods that would be much more difficult to work with in more complicated environments. So this is what our study of membership looks like for a given association. So we, as I mentioned, we have complete RV coverage above the premium sequence turn-on, which is right here. So all of these stars have spectroscopic results from our studies, and you can see that we can kinematically reject a bunch of stars based on the fact that they do not have, they are not co-moving with the association as a whole. And then, as you get further down, you get this big chunk of yellow stars here And these are stars that are high enough above the main sequence that we can identify them as young just by virtue of their position on this diagram. That obviously stars that are on the main sequence, on the field main sequence, can be rejected photometrically. So this is what we get when we take Cepheus far north and we look at it in terms of substructures. So for this, we use the same sort of method that we use for SPYGLASS 1, and that is using the HDB scan clustering algorithm to identify substructures. And in this case, we get 7 of them, and they're distributed all around the association. They all have distinct kinematics and have, at least somewhat distinct positions in spatial coordinates. One interesting fact that we get here is that we actually find a very low metallicity for this association. So there's a collaborator of mine that his name is Simon Murphy. He works on astroseismological studies of stars. And through his work on a few members of CFN, he found a metallicity of negative 0.3, which is a record for a young solar population in the solar neighborhood. So if that does turn out to be the case, and we're working on doing some metallicity studies using my spectra as well, that could be a very important thing for future studies. And we've got the good RV and lithium coverage, so we can start to look into whether we can get dynamical ages from the motions of these stars, whether we can get lithium depletion boundary ages, well, not the boundary ages, but the lithium depletion on the higher mass stars. And we can also use isochrones to get a sequence of formation from the association. That can be tricky because the models can vary quite a bit, but in terms of what stars are higher on the sequence than others, it can give us a very strong comparative indicator of what stars form before the others. So first thing first is the dynamical ages. So basically what we did was we implemented a traceback method. This is using GalPy, and we use the Milky Way potential to trace these stars back in time. And it turns out that when we do this, with only a couple of exceptions, we get a very distinct minimum in the distances between stars in the past. And basically the idea here is that that point of closest approach is where the stars originated from. So you can see that we sort of get like 2 main clumps of formation appearing in this diagram here. We've got one at around 15 million years. We got one at about 21 million years. And then we have 2 that are sort of outliers and a little bit bizarre. And these are cases where the dynamical ages are perhaps not the best use or not the best indicator of age. One here has only 3 stars, so it's not really the best sample size to work with. And this orange one here is actually, it turns out to be likely a bound open cluster. And when an association is bound, this sort of breaks down because of the fact that we have gravitational binding holding the stars in, so that prevents this sort of naive, dispersal assumption from working. But you can see in all these cases, we seem to get, or in all these other cases, we seem to get relatively convincing minima from doing this traceback. And a great way to determine whether one method is working well is by comparing it to others and seeing whether that is able to replicate similar results. And when we do that with the lithium depletion, we actually get a fairly similar result. So you can see here that I have the Cepheus far north stars, which are in this dark blue color. And if you compare them to other populations, it looks as if the majority of them are right along this section here, which is associated with the Upper Centaurus lupus section of Scosan. And this is assumed to be at about 16 million years old. And you can see that they more or less align with that section of that sequence. However, there are outliers. And they are down here, and they're closer to the Beta Pictoris sequence. And it turns out that the stars that are down towards the Beta Pictoris sequence are actually more similar. They're actually members of the same populations that we identify as being older through dynamical ages. So you can see here that we have 16 million more or less lines up, and about 23 million lines up right here. So that's giving us about a 7 million year spread in ages, which is the same as what we see from our dynamical ages. It's shifted a little bit to the older side in time, but it's still a very close replication of what we're seeing in dynamical ages. And same idea with the isochronal ages. So we're getting 13 to 17 million years using that FE over H of negative 0.3 measurement. And the order of the formation for all of the cases where we have a good dynamical age is exactly the same as the order of formation that we get from looking at the dynamical ages. So it's a very good indicator that our dynamical ages are doing the job. And because of the fact that we have ages plus the motions of these stars, we can begin to view the locations of these stars at the time of formation. So I'll show you what that looks like. I have a video for you. So this is what the formation of the association looks like when you start each section of the association from the assumed age based on all three of these age determination methods, and we allow it to move forward in time and allow clusters to pop in as we infer that they have appeared. And you can see, first of all, that there are two sort of locuses or loci where we have stars forming. So we got one down here, which begins with the beta Cephei cluster, which is this purple one here. And we have a second burst of star formation that begins early in this upper node. And that starts around the EE Draconis cluster, which is that bound cluster that I mentioned doesn't have a good dynamical age. So what appears to be happening here, we have two generations of star formation in each of these nodes, both of which are connected to a burst of star formation that includes the brightest and the second brightest member of this entire association. So we get beta Cephei forming first alongside E Draconis, and then there's a pause. And then the star formation starts up again in both of these nodes. So what we think might be happening here is we could have, gas flowing into these clumps. However, when the first burst of star formation takes place, this is the one that forms E Draconis and forms beta Cephei. We could see the feedback from those solar populations briefly dispersing the gas before it's able to recollect and able to form stars once again. So that appears to be what we're seeing here. At least that's the active explanation. But yeah, it seems as if we're getting a very detailed view of how star formation has progressed here, and it could give us very important insights into how the processes that shape star formation lead to outcomes in terms of star populations. All right, so our next population that we are currently working on targeted studies for is this group called Fornax horologium. It is more or less closely related, or possibly another way of saying the Chi-1 Fornaxis cluster. And the core Chi-1 Fornaxis or Lessee 13 cluster is this little clump right in the middle, but we see a significant structure around it, so that gives us a bit more to work with. And there does appear to be some tenuous structure that possibly emerges. However, this is currently a little bit up in the air. We're working on tweaking our clustering algorithms to get as much as we can out of this. But for now, what is most important is its potential relations to other associations. So there have been quite a few nearby associations that have been proposed as being related to our Fornax horologium group here. And those include Tucana horologium, Columba, and Carina. And when we look at the ages from isochrones for Fornax horologium and Columba, which turns out to be very similar, it appears as if their sequences lie directly between those of Carina and of Tucana horologium. Carina being in about 22 million years, and this is corroborated by Livian depletion and by dynamical ages, and Tucana horologium, which is getting about 40 million years using the same methods. And with Columba and Fornax horologium right in between, it appears to have about a 30 million year age is likely accurate for that population. So this gives us same as Cepheus far north, a population where we have a sequence of star formation, where we have the ages and we have stars with 3D motions measured using our shell spectrographs, and we can try to trace back how these stars formed. So I'll do this in a still frame version this time, but you can see that our work is indicating that Tucana-Horologium, which is this brown color, formed at around 40 million years. And as time went on, we got a second burst of star formation in a fairly distinctly different region that was associated with Fornax Horologium and Columba. And then at about 20 million years, again co-spatial with Fornax Horologium and Columba, we get another burst of star formation associated with Carina about 10 million years later. So this sort of rhymes a bit with what I was showing to you about Cepheus far north, right? Is in that we have 2 loci where we form stars, and one of them has 2 distinct bursts of star formations associated with it. That is Fornax Horologium and Columba, followed by Carina. So we seem to get this sort of pattern emerging in some of these associations where we have, multiple bursts of star formation in multiple loci. And another interesting thing to note, and this was actually the case in Cepheus far north too, is that these associations appear to form almost exactly as they cross the galactic midplane. So we can see that right here we have, Tucana-Horologium forming just as it crosses the midplane, and then same thing for Columba and Fornax Horologium. Carina is still close to the midplane when it forms. However, that may be dominated more by feedback by Columba and Fornax Horologium rather than interaction with the midplane itself. So this is an interesting fact that we're seeing emerging. And it could indicate that perhaps feedback processes or shocks with the interstellar medium may be sort of inducing infalling particles of gas to form stars as it crosses the galactic midplane. And speaking of things that are infalling, we have a few associations emerging that have very odd positions. Typically we expect star formation to take place in the midplane. Well, we have a few outliers, one of which is this Leo-East association right here, is actually very extreme. So you can see here that this is, the main component, which is this dense clump up here, is more than 300 parsecs above the galactic midplane, which is, absolutely bizarre when it comes to, a young association. Typically, we only see much older associations in these bizarre positions. So how might this have formed? Well, let's take a look at its properties. So first of all, dynamical age appears to be about 11.5 million years, which is very young. And if you do the traceback on this, that turns out to be within 1 million years of when it crossed the galactic midplane. So again, we're seeing that pattern continue. We want to see, we have some lithium coverage on Leo East as well, although it's somewhat inconclusive because of how large the error bars are on these stars that really, are able to differentiate between different amounts of lithium here. We have 2 subgroups associated with this cluster, one of which is about 4 million years younger. And if you do the trace back on that one also crosses the galactic midplane at about the same time. So it appears as if they, both cross the galactic midplane with about 3 million years of formation with a mean vertical velocity of about 26 kilometers per second, which is incredibly fast. So, we want to get a metallicity on these as soon as possible, and we're currently working on this. And, one of the active theories is that there are some known gas parcels that exist at high velocities well above the galactic plane, and the idea is that we could have some of these falling through, forming stars as they go and just shooting out the other side, and allowing there to be this population that exists at a very extreme position as a result of that infalling material. All right, so that does it for what I'm currently working on in the case studies section. However, there are quite a few that I am sort of working on or preparing to get to the next level and get it to the point of getting papers out. The first of these is Perseus. So I mentioned that Cepheus far north and Fornix both had evidence of multiple bursts of star formation in multiple sort of sub-nodes of star formation. Well, in Perseus, we have something very similar. So we have two subgroups that are clustering identifiers. We have this group number 1, which includes NGC 1333, and group number 2, which includes IC 348. And it turns out that both of these subgroups have their own, sort of two-sided structure here, where we have a dense clump towards the west, which contains much younger stars, and we have a sparse, dispersed clump to the east that contains much older populations. So this could be an example of, once again, multiple generations of star formation that are caused by the initial formation of hot stars or possibly even supernovae. So we get that same sort of idea of this repeated star formation interrupted by an initial star forming event. And we have applied for Gemini Grace's time. Hopefully we get that. That'll allow us to get lithium depletion boundary ages on these, which are much more accurate and can hopefully give us a very accurate view of what the ages are on these older populations and whether they are consistent with the sort of age that we expect out of them. Okay, the next population that is of a lot of interest is SCO-SEN, and this is one that I focus on a lot in my SPYGLASS 1 paper, where we looked at all these populations and did an overview of a few of them. And SCO-SEN has what appears to be an old arc of star formation. This is formation that is older than about 20 million years. All of these clumps right here have that old age, and they all form into the same arc. And as we go away from that arc, that is, we go down towards this branch of LCC, as we go out in this direction towards TW Hydra, and as we go out in this direction towards the subgroup that I call SC11, we see that we get increasingly young ages moving off this arc. So what appears to have happened here is that we've had a large star formation event that takes place along the circular arc. And then we have a sort of sequence of formation where we have, stars from the initial star forming event, introducing feedback into the system, compressing the gas in front of them, and sort of, form stars, compress, form stars, compress, form stars, compress. It's this wave that passes down a molecular cloud and creates these sort of sequences. So that's the active explanation there. However, as you might have noticed, there's this whole mess, which is completely chaotic. It doesn't really follow clear patterns. So what we really want to do in the future is try to figure out exactly how the formation sequence happened for all of these components, how we get, the newborn lupus cloud right here between two older populations, how, Kerr Australis exists, how SCO-SEN is this big population of stars that's been forming stars for quite a long time. There's a lot that is still to be known in SCO-SEN about how the star formation progressed. And we've been working on gathering a lot of spectra to do exactly this. So I got time at the LCO, so Los Cumbres Observatory, the same one that I'm using for some of my other populations. However, when you have a population with about 10,000 stars or more than 10,000 stars, having only a few hundred from a single pointing telescope is not really great. So what we've been doing is getting AAT times, the Anglo-Australian telescope. It's an integral field spectrometer that allows us to observe up to 400 stars at the same time. And that's allowed us to get over 1,000 additional spectra, which will give us an incredible ability to, trace back the motions of stars in SCO-SEN. So just a bit of a summary here on this whole section about these population case studies. We have a ridiculous diversity and complexity in nearby star formation. So these are all populations that I've shown interest in so far. And there's really like far too much for me to be able to handle on my own here, or at least on a short time period. So there is so much available to be studied when looking at these nearby populations that it's quite frankly overwhelming at times. But we already have some very exciting new patterns of star formation emerging. These include multiple loci of star formation taking place in Cepheus far north, in Leo East, in Perseus, in Fornax Horologium, all these different populations. We have star formation pauses, sequential star formation, scope stand, all these different features that could indicate unique star formation processes. And we also start to see patterns of potentially low metallicity formation in cases like scope stand, and also cases where we have formation as clumps pass through the galactic plane. So that's another feature that we might want to look into in the future. And once we start getting metallicities back for these associations, determining whether they are consistent with the sort of parcels of gas that we see as potentially infalling in these other studies. All right, on to the survey section of my presentation here. So as I mentioned before, the SPYGLASS 1 paper, which is the initial paper that I published over the summer, was this study of young populations within the nearest 333 parsecs to the sun. What we're wanting to do now is using the EDR3 and DR3 Gaia data expansions to try to expand our study out to about a kiloparsec. And this is what it currently looks like. So there are a few notable features that I'll go into more detail on in a little bit here. And these include a merger of Perseus, Monoceros South, and Orion. So we have this sort of like mega Orion association emerging here. Whether this is real or an artifact of projection, that remains to be seen. We're currently working on that. We also have this feature here called Zephyr, which is an emerger of a few populations that we identified in SPYGLASS 1, including Cerberus, Lyra, and the Cepheus Cygnus Association. And we also have, just in general, 230 groups using the original Gaia distances. And a recent update is bringing more than 300 using Baylor-Jones distances. And final results on that are pending, but hopefully we can start to make those public fairly soon. We're getting pretty close to being able to do that. So there are a few updates still planned. So we want to update the Redming grid. So as of right now, we have to de-redden the stars using the Lallemant et al. Maps. And those are excellent for, especially in like low reddening environments. However, behind molecular clouds, you often see that you get this streaking effect. So this here is the Serpens cloud. Then you can see behind it, there are all these little clumps that are, all coloring up the region behind it. And most of these are likely not, in fact, real associations. A lot of these are probably just artifacts created by the fact that we have this big cloud in the way that is heavily reddening stars and bringing stars that would have originally been on the subgiant branch down into the region where we identify stars as being young. So we want to try to, improve the reddening handling that we're currently using. And we also want to vet associations to try to remove any anomalies that may remain afterwards. And on the topic of merging associations that possibly shouldn't be merged, we want to try to refine what the background is and try to determine whether our merging populations is appropriate. So that's something that I'm going to be working on quite soon. Now, what do we want to do with all this? Well, there are quite a few possibilities. So first of all, we have, we got a large scale view of this. So, there have been recent studies that have done investigations of big gas structures in the solar neighborhood. And one of these has been the Radcliffe Wave, where we have this big, kiloparsec long line of dense clouds that runs essentially along this axis right here. Now, what we're wondering is whether there is anything similar to be seen in terms of star formation. Now, we need to do a lot more work on this to really get a good view, and looking at this in terms of not just the positions of stars, but also their ages. So we want to see if there's potentially like a sort of a pattern in age across our populations that could be indicative of potentially a propagating Radcliffe wave. So, that's something that we want to look into very soon. Further down the road, we want to look into an initial cluster mass function. So this is looking at the populations of associations at individual sizes. So see what sort of pattern we can get out of the sizes of the populations as a function of their sizes, as a function of their populations. And we also want to just get like general statistics on star formation patterns. Let's say, do we see sequential star formation happening in large environments and small environments? Does it only take place in groups that are large like SCO-SAN? What are the limiting factors as to what sort of mechanisms are dominant in terms of star formation? And of course, as we identify more and more populations, we can begin to characterize new ones, and that's what I'm going to go into right now. So one population that we are currently working on is the Zephyr Complex, which I mentioned before. It has over 10 to the 4 candidate members, spanning about 250 parsecs, with an age mainly within 10 million years of the mean age of the association, but with extreme cases at about 20 million years. And you might notice that these are fairly similar numbers to what we see in SCO-SAN, where we have, again, about a 20 million year span in terms of ages at the extreme end. We get a size that's actually a little bit smaller and a population that's about the same. So it appears as if this may be a good older analog for SCO-SAN that we can use in a lot of comparative studies. And I mentioned that Luke Bouma had found some planets in the population that I discovered. It turns out that that population is actually this subgroup number 2 here. And there are a couple of planets in this one. They are, they're showing all the youth indicators in their light curves in Kepler. And there is a paper that is currently very close to publication that is highlighting the properties of these planets. So lots of opportunities there. And another thing to note is that this population is actually perpendicular to the Radcliffe wave. So the question is, if we have a sort of dominant axis of star formation going in this direction, why do we get something like this? And that could be an interesting study as to how a population like this came to be. Now, before I leave you here, I'm going to quickly go over just a single case study of the sort of power associated with the method that I'm using here. That is the method of identifying stars, identifying populations, identifying substructure, and identifying the ages of that substructure. So there was some research done by Peng et al., a researcher at Xi'an University in China, and she identified a sequence of star formation, sequential star formation in this region of the Dynamical complex, going along this axis here. And I was curious as to whether I was able to replicate this and sort of, corroborate the research done by Peng et al. And it turns out, yes, absolutely. This was basically just spat out directly by my algorithm. I didn't have to do anything with it. I just took the data out, plotted it, and you can see that I'm already picking out these sequences of star formation going from an original origin and smoothly increasing in age out to minima along the edges. So you get this sort of like 3-branch structure to the populations in Vela, where it appears as if sequential star formation is happening along those axes where we have feedback, compressing gas, forming stars, compressing gas, forming stars, and so on. So this just goes to show the ability of this study to rapidly investigate populations and do so with very little additional effort. So it just gives us so much opportunity to study populations in bulk and learn so much about the processes that drive the star formation. Okay, just to conclude here, so SPYGLASS 1 has revealed many new structures and features that merit follow-up within the 333 parsec distance. These include populations like Cepheus far north, which shows unique star formation patterns, including a pair of simultaneous star forming events, and a pause after the first formation wave, similar to what was seen previously in Perseus. we have emerging patterns of formation across the galactic plane, and potentially low metallicity formation in low mass associations like Cepheus far north and Leo east. An expansion of our survey to 1 kiloparsec is underway to using the Gaia DR3 and EDR3 expansions. And intriguing forming patterns are everywhere throughout our surveys in both known and unknown populations, producing a rich data set for further investigation of young populations on both a local and a large-scale statistical method. So thank you all for listening to me. I would be happy to take questions now. Thank you.
Thank you very much, Ronan. Let me ask if there are any other questions from the people.
Nothing?
If not, if not, there's a thanks for a great talk. What are the errors in the age parameter of the associations, and how did you identify the members of associations?
Yeah, so I'll start with the second one. So the members of the association were identified using the H2B skin clustering algorithm. It's the same thing that was used in SPYGLASS 1. So this is, we take the population of, in SPYGLASS 1, 30,000 stars, in our upcoming expansion, about 180,000 stars. And we apply this clustering algorithm that works on XYZ space and transverse velocity space. I realize I might have not explained that all that much, so apologies for that. And this allows us to get clustering that works on both the spatial dimensions and on the velocity components in the direction of the sky. So unfortunately, because of the fact that Gaia only gives near complete coverage on the plane of the sky astrometric component, it turns out that if you use the Gaia RVs as well and try to get like a three-dimensional motion, you lose a lot of data that way. So it can be more useful just using the instead using the dimensions on the sky plane. So we cluster on the sky plane dimensions, transverse velocity, plus the spatial components. That gives us a very strong ability to identify large-scale clusters, and then to identify subgroups within those clusters once we delve deeper and try to identify subpopulations. In terms of the errors associated with the age parameter in the associations, that's also a tricky thing to assess, just because of the fact that, especially when we're doing isochronal age estimates, the model is by far the dominant factor when it comes to the uncertainty in ages, when it comes to these populations. So, for example, if I use the parsec version 1.2s isochrones with a metallicity of 0, so that is, solar metallicity. If we use that as a model for Cepheus far north, we get populations that show ages in the neighborhood of about 30 million years in some cases. Now, if we do the same thing and we use the BHAC 15 models, we get something closer to about 13 million years. I think we actually got some lower. I think it was like 11 for the younger populations for the BHAC models. So massive ranges there. But what's important for our purposes is that we have other methods that allow us to sort of constrain the range in which these models could possibly exist. So we have this sort of sequence of formation from the isochronal models, and I trust the order of the ages much more than I trust the absolute ages. But then we have these dynamical ages and these lithium depletion boundary ages, or lithium depletion ages, which allow us to sort of constrain where that sequence is and say, okay, is the 30 million year range feasible, or is it something that is dictated by the dynamical ages as being closer to the 14 to 20 million year range? So that's the sort of thing that we use, just try to handle those absolute error problems.
Okay, thanks a lot. Are there any other questions, or? I actually have two, Ronan, if you don't mind. First of all, when you say you were using some algorithms to separate the clusters or associations, let's say in the X, Y, or plots? Is it like something like this DB scan type of algorithms that kind of use machine learning and stuff, or is it? Do you also rely on? I thought you are like whether if the I mean the location of the star in the, let's say, color magnitude diagram and so on. Like, is it just?
Yeah, so we only cluster based on those XYZ and transversal velocity components, and we do use HDB scan. So HDB scan is similar to DB scan, but
Yeah.
rather than picking a single scale to cluster over and just saying if it like exceeds the scale, we count that as being a clump. What HDB scan does is it looks at all the different scales and basically picks the clumps that are most persistent through different scales. Let's say you have you got this clump which with a density profile that looks like this, right? Or we have this big, we have a cluster that emerges over a lot of different scales. Then we have some small subcomponents that exist only at larger scales. So what HDBSM is going to do is it's going to say, well, this clump exists over all these scales. So what we're going to do is we're going to merge that as being a single clump.
I see.
And merge it at that scale. However, what we do with subclustering is we then look at, okay, we've got these two little peaks on top of that cluster. So what we want to do now is we want to, now break off these subcomponents and say we've got this subcluster and this subcluster all existing within this big clump that exists because HDB scan is identifying it as the most persistent clump in the population. That's how our clustering works. I realize I glossed over that a lot. There are a few things that I sort of skipped over for the sake of brevity and getting into recent results. But yeah, if you want to look into this more, feel free to look at my at the SPYGLASS 1 paper. It's a bit of a marathon. It's like a 50-page document with a lot of a massive amount of discussion of methods. It's got like 25 pages of methods. So if you really want to get into the weeds on that, that's where I recommend that you go. But hopefully my explanation was reasonably comprehensible.
Oh, no, thanks. Perfect. Thank you very much. The final question I had was that, like, we usually, I mean, at least myself, who is not really working on this star formation and stuff like that, kind of assume that, if a star or if it's an association or whatever, if it is young, then metallicity should be kind of, relatively larger. If it is old, then it's low metal. So I was surprised to see that metallicity that you were showing with the ages. I mean, would it be possible for you to kind of, let's say, elaborate on this a little bit? Is it common to see these kinds of low metallicity young associations? I really don't know.
Yeah, so it's not common at all. Is the quick answer there. So when I was doing my sort of Bayesian analysis for like identifying members of a cluster and separating them out from field members, what I actually did was I took a population with a metallicity centered on 0 with a 0.1 sigma to it, which is roughly what the population is you assume that it is centered on 0 with a 0.1 sigma, which is very, very tight. So the extreme examples that exist include things like, I think Persepi is what, -0.2 or something like. I could be mistaking that for positive 0.2. But I know that Persepi is one of the outliers, NVC 2516 is another one, but they never go beyond 0.2 in either direction.
I see.
Now we're seeing Cepheus far north at -0.3. Now, my personal suspicion is that the populations that have been studied to date have only focused on the big populations because those are the ones that we can see well. So this includes like Scosen, the Pleiades, Persepi, Hyades, all these populations that are easily detectable. However, the populations where we're seeing evidence of lower metallicities are all very small associations.
I see.
In fact, they're all associations that are isolated and appear to have just passed through the galactic plane, formed stars, and continued on to fairly low or high galactic latitudes. So it appears as if it could just be a matter of selection bias, whereas we're seeing the populations that are coming from well-mixed gas clouds where we have metallicity that has been enriched by star-forming events in the galactic plane. And then the stars that we're looking at are from gas clumps that come from very different origins.
Nice.
That's why we're seeing what we're seeing.
All right. Okay. Thank you very much. Now, so in time, I can say then I guess we will see more of these probably, right? I mean, with the
Quite possibly.
Yeah. Okay.
Yeah. So I've got another 7 of these like isolated small associations that I've got in the queue. I'm starting to work on dynamical ages and isochronal and lithium depletion boundary ages for all of them. And I have some people that do metallicity. So the idea is we're going to start to try to get as much metallicity coverage on these associations as possible, and hopefully write a paper within the next year or so, just detailing, metallicity, age, formation, location, all those properties across all these associations that we've identified. So that should be a great study to sort of answer some of your questions here and see whether this is in fact a real thing, or whether we're just sort of, extrapolating a little bit too much from a single data point from a single source. So we'll see how it goes.
Yeah, sure.
There's a lot to look into here.
Okay. So if there are no other questions, I don't see any. I thank you very much, Ronan, one more time for this very nice talk and for the very nice studies. And
yeah, no worries, of course. Thanks for having me.
Yeah, thank you very much. Bye.
Bye.
Have a good day, guys.
Kesin demem çünkü niye demem kesin. Bizden abi